We have already learnt that any two charges can exert a force on each other whenever they are placed at a distance. But how do these charges exert this force without even touching each other? Our objective is to understand the concept of electric field. The force between two electric charges is proportional to the product of the two charges and inversely proportional to the square of the distance between them. Just as the gravitational force between the two masses is proportional to the product of the two masses and inversely proportional to the square of the distance between them. These two laws for electric and gravitational forces have similar mathematical forms. Here G is the proportionality constant for the gravitational force and 1 upon 4 pi epsilon 0 is the proportionality constant for the electrostatic force, where epsilon 0 is the permittivity of the free space. The action between two charges, masses or magnets kept at a distance describes some of the characteristics of these forces, but does not really explain how these results are achieved. The critical question now is, how is each mass or charge or magnet aware of the other? This question was addressed by Michael Faraday, who proposed the concept of field, which we shall see next. Electric field. The space surrounding an electric charge has a property known as the electric field. This electric field exerts a force on other electrically charged objects. To define an electric field, consider a point charge Q called source charge, where Q is greater than 0, and place a positive charge Q0 called the test charge at some point, say P, at a distance r from Q. The electric field at P due to the charge Q is vector E is equal to vector F over Q0. The test charge should be as small as possible so that it does not affect the source field. The direction of the field vector E is that of vector F. The electrostatic force vector F that acts on Q0 is vector F is equal to 1 upon 4 pi epsilon 0 times Q0 over r square into r cap. Or the magnitude of vector E equals F over Q0 is equal to 1 upon 4 pi epsilon 0 times Q over r square. The electric field due to any single charge is inversely proportional to the square of the distance from that charge. As the magnitude of E equals F over Q0, the SI unit for the electric field is Newton per Coulomb. Thus, vector F is equal to Q0 times vector E. That means that if the charge on the particle is positive, the electrostatic force acting on it is in the direction of the electric field E, and if the charge is negative, the force acting on it is opposite to the electric field direction. Electric fields follow the superposition principle. If more than one charge is present, the total electric field at any point is equal to the vector sum of the respective electric fields that each charge would create in the absence of the other charges. Let's summarize what we have studied. Here we learnt that an electric field is the physical field that surrounds each electric charge and exerts force on all other charges in the field, either attracting or repelling them. Mathematically, it is defined as the electric force per unit charge. Its SI unit is Newton per Coulomb, and it follows the principle of superposition. While the electric field due to a charge is invisible, It is visualized using electric field lines. Stay tuned.